Hello, welcome back. From the very beginning, we have been saying that in a SEM study, you propose a hypothesized model in which causal relationships between variables are included. Then you test your model to see if the proposed model structure is supported by observed data. However, you need to keep in mind that even if your model have good fit indices, it is only one of the plausible hypotheses out there that can explain the data structure at an acceptable level. Therefore, it is important for you to have open mind about other hypotheses and whenever possible, test your model against some other competing models. The focus of this video is about model comparison. We will talk about how different models are related and have a brief discussion about model training, model building, and how to use modification indices in your model respecification. With a good understanding about the theories related to your research, there are two different approaches in your model specification. One is called model trimming, and the other is called model building. In model trimming, you usually start with a model in which all potential paths are included and delete those non-significant paths to improve the model fit. In model building, you take the opposite approach. Usually, you start with a bare-bone model in which only the paths you are most certain about are included and add additional paths to improve the model fit. No matter which approach you're going to use in your own research, just keep one thing in mind. Any changes you make to your model should be theory-driven. Now, let's consider the situation in which your model has good fit indices and you are able to identify alternative models that also have good fit indices. It becomes important for you to compare your model with alternative models to see which model fit the data better. In order for you to make appropriate comparisons, you need to know how your model and the alternative model are related. There are three different types of scenarios. First, the models are nested. Second, the models are non-nested. And third, the models are equivalent. When two models are nested, the parameters of one model is a subset of the parameters of the second model. For example, the two models here on this slide, Model 1 and Model 2 share all the variables, and everything you see in Model 1, they are part of Model 2. However, Model 2 have this correlation between exercise and hardness, which is not part of Model 1. So in this case, Model 1 is considered as nested within Model 2. When you compare two nested models, you look at the difference between the model chi-square values. If the chi-square change is statistically significant based on the change in the degree of freedom, you would say one model is significantly better than the other. Based on the example I have, I ran the analysis of the two different models. For Model 2, in which exercise and hardness is correlated, the model chi-square is 11.107 with a degree freedom 5. For Model 1, in which the correlation between the two exogenous variables is removed, the model chi-square value is 11.443 with a degrees freedom of 6. The difference between the two model chi-squares is only 0.336 with a degree of freedom change of 1. Either a critical value table or an online calculator can help you to figure out when degree of freedom is 1, the chi-square critical value is 3.841. Because the chi-square change is lower than the critical value, it serves as evidence that Model 1 and Model 2 have comparable fit. However, Model 1 is simpler than Model 2, so we would choose Model 1 as our better model. You can identify a better model by comparing model chi-square values in both model training and model building approaches, because in both cases you're comparing nested models. When two models are non-nested, neither model has a set of parameters that is a subset of the other model. Look at Model 1 and Model 3 on the slide. You can see that in Model 1, there is a direct path from fitness to illness that is missing in Model 3. However, in Model 3, there's a correlation between exercise and hardness that is missing in Model 1. Also, in Model 3, there is a direct path from fitness to stress, which is not part of Model 1. When two models are non-nested, you cannot use model chi-square values to decide which one's better. Rather, some kind of descriptive model fit indices should be used to compare non-nested models. In the example here, I used AIC to compare the two models. For Model 1, the Mplus output shows a AIC value of 19906.883. For Model 3, the AIC value is 11964.771. Models with lower AIC values are considered as better. So between the two models, Model 3 is perceived as fitting the data better than Model 1. I'm going to repeat myself one more time here. Before you compare alternative models, you want to make sure the models you're comparing both have good fit indices. The third scenario is in which when you have two models that are equivalent to each other. For example, Model 1 and Model 4 look different. In Model 1, there is a correlation between exercise and hardness, the two exogenous variables. In Model 4, they are related, but there is a direct path, structural path from exercise to hardness. However, when two variables are related, whether they have a correlation or have a causal path doesn't make a difference in the model evaluation. In other words, they are considered as equivalent because they will yield the same goodness fit indices. You would have to decide between the two models based on theoretical considerations, not statistical evidence. So far, we have been assuming that we are lucky enough to always find a model of good fit. That's not the case in real life. Oftentimes, you propose a model and end up with disappointing fit indices. You may have to read more literature and make changes based on new information, or you need to rely on empirical evidence, such as the model modification indices provided by the software. I analyzed this model in Mplus. Remember, in the command file, in the output block, there's a line that says mod indices. In the parentheses, I put in a number 4. This is a request to print the modification indices in the output file for any changes that will decrease the model chi-square by 4 or more. In the output file, if you go to the bottom, there is a section called Model Modification Indices. There's a line reminding you that the minimum MI value for printing the modification indice is 4, which is a value I requested. You can decrease to 3, raise to 5. That's a guideline value provided by the textbook. But I know for chi-square, when the degree freedom is 1, the critical value is close to 4. That's why I use 4 here. 3 possible changes are proposed here. Each of them will decrease the model chi-square by 4 or higher. Keep in mind you only want to do one change at a time. My suggestion for you is to start the one with the highest decrease in chi-square value. So in this case, it's 5.372. If you add a pass from stress to fitness. Before you make any changes, the first question you would like to ask yourself is whether this change theoretically and or conceptually acceptable. In this example, I think it makes sense to add a path from stress to fitness. So I may make this change, but the second thing to keep in mind is how much improvement this change will bring to your model. The fit indices of the current model, before I make any changes, are at an acceptable level. For example, the model chi-square is 11.107 with a degree freedom of 5. It is statistically significant because the p-value is lower than 0.05, but it's very close. The RMSEA is lower than 0.06, CFI is greater than 0.95, and SRMR is lower than 0.06. After I make this change by adding this proposed path, the model chi-square value decreased to 5.68 with a degree freedom 4, which is statistically non-significant. RMSEA is really low now. It's lower than 0.04. The CFI is close to 0.99. And the SRMR is only 0.03. The fit indices look better, and this change would be strongly recommended if the original model did not have good fit indices. In our example, both the original and the modified models have acceptable fit indices. So the decision will be on you as a researcher to decide which model is theoretically and or conceptually more suitable to your research purpose. You can make further changes to your model in order to improve the fit indices. However, in our example, after you make the first changes, adding that pass, the other modification indices are gone. There's no more further suggestions. A few more words for you to remember. First, any changes you make to your model should be theoretically and or conceptually acceptable. Second, if you choose to use the modification indices, make sure you start with the one that gave you the greatest reduction in the model chi-square value and only make one change at a time. Remember that model modification indices are empirical information from your sample data. So learn from your data, but your data should not be your teacher.